Hello and welcome to another lecture session of Introduction to Astrophysical Fluids. In this session, we will discuss very briefly some interesting aspect of MHD equations. So, magnetohydrodynamics, as we have seen, that it consists of the continuity equation, the momentum evolution equation of a of a charged plasma, right, a plasma monofluid. Then comes the induction equation, and then we have also a generalized Ohm's law, okay, and finally we have a closure, which for instance we use the polytropic closure or isothermal closure. Now we want to see that in different limits how these equations would behave. So the first one is, as we did for hydrodynamic case, we discussed the fluid property when it is at rest. That was the case of hydrostatics. Here similarly we will discuss the properties of a magnetic fluid at rest, and this is known as magnetohydrostatics. Okay. So for magnetohydrostatics, of course, the fluid velocity v is equal to 0. So if you just replace that in the momentum evolution equation, you will simply have rho times F. So where F is the body force density minus gradient of P, the pressure, plus curl of B cross B by mu 0, right? So that is the Lorentz force term. Both the del V del T term and the inertial term and the I would say this one, because this is the dynamic viscosity, and this viscosity term all are vanishing because the V is vanishing. Okay, so as you can see, this is the case where we have V is equal to 0. So the sum of these three is equal to 0. And for the magnetic field evolution equation, we in general have del B del T plus del B del T is equal to curl of V cross B plus eta times nabla square B. So here when V is equal to 0, simply we have del B del T is equal to eta nabla square B. So which is nothing but an equation of a simple diffusion. So when the system is at rest, the fluid is at rest, then the magnetic field would simply diffuse. Okay, and all the three forces, body force, pressure gradient force, and the Lorentz force, they balance each other just by giving a net contribution of 0. Okay. Now when the body force is very small, for example, most of the cases in space and astrophysical cases, if the gravitational force is very small with respect to the pressure gradient force and the magnetic force, okay, magnetic force, and Lorentz force, okay, for a system, then for example in a solar surface, this is a very good example for that. Then this term can be neglected and we simply have a balance between these two terms, and that's exactly what is written over here. That is, the nabla P or gradient of P is equal to curl of B cross B by mu 0. Okay, now I can divide this total term into two parts, since one part can be absorbed in the pressure term. Okay, so this is the magnetic pressure part and this term is nothing but the magnetic tension. Okay, so here we can see that in this situation the total pressure gradient force is exactly balanced by the force due to magnetic tension. Okay, so in this situation the magnetic field is known as pressure balanced field. Okay, and not in a very straightforward way, but if you just follow some steps, actually one can show that for just trying to solve this this type of equation, okay, for cylindrical symmetric case, you can actually be led to some instability, which is known as sausage pinch instability, and that is a very familiar instability in some places of solar coronal plasma. Okay, so here I am just mentioning you all the a number of cases where you can simply see the direct application of magnetohydrodynamics or of course, limits of magnetohydrodynamic equations. For example, here we are in the static case. And then if you are interested furthermore, you can actually search over internet or in various books. You can go into the detail, and if you have any question, you can ask me always. So after this step, if you follow this step, you can simply see that there is finally we have a grouping of the terms in a pressure type of term and the tension term. So inside the pressure type of term, finally you can again say that if we have a plasma whose beta parameter is very small, that means the magnetic pressure part dominates largely the kinetic pressure part, then you can simply neglect this pressure term with respect to this one. So finally you have gradient of b square by 2 mu 0 is equal to b dot gradient b by mu 0, and which is nothing but equivalent to writing curl of b cross b is equal to 0, right? And that simply means that curl of b and b, they are parallel, and this is just nothing but an alignment between j and b. Okay, if you are familiar with Beltrami alignment, you can easily understand this is also a type of alignment. So Beltrami alignment is an alignment between v and curl omega, that is v and curl of v. So here exactly we have a Beltrami type of alignment for b and curl of b. Okay, and what is the meaning of that? That means that j cross b is 0. Okay, because this is equal to this also. When this is 0, then this is also 0. So the Lorentz force term basically vanishes. Okay, here should be in principle one vector sign. Okay, yeah, so Lorentz force vanishes, and that's why we call this as force free field. The corresponding magnetic field is known as force free field. Okay, now if we have this situation, then of course we can say that curl of b can be any scalar times b. Okay, so that's the because they are two collinear vectors now, so one vector can be written as a scalar function times this vector b. Okay, then you take the divergence of both sides. So in this side, this is a divergence of a curl which is 0 identically. So in this part, that will be divergence of lambda times of b, which is also 0. Now remember, lambda is a scalar, so it can be a function of space as well. Okay, I am not saying lambda is a constant, I am just saying that lambda is a scalar. So divergence of lambda b is equal to 0. It simply says, since divergence of b is always 0, then this is equivalent to writing b dot nabla lambda is equal to 0. So that means that if you are following one specific magnetic lines of force, then along these magnetic lines of force in space, lambda's value does not change. So for every lines of force, you have a specific value of every magnetic lines of force, of course, you have a specific value of lambda. Okay, so lambda cannot vary along a magnetic field line. Of course, from one magnetic field line or lines of force to another magnetic line of force, it can change. Now there can be a very simple case, okay, that let's say we are in such a system that lambda itself is an absolute constant of the system. So that means it is constant everywhere. Okay, it is constant over all the magnetic lines of force. In that case, we can simply say that curl of b is equal to some constant times b, and this specific case leads to the magnetic field, which are then known as linear force free field. Okay, So why these are important? Because this type of alignments are very much true for most areas in the solar corona. So in some areas we have seen in the solar corona we have pressure balance, but in the most area we have this force free field, and you can see that this is an active research, this is a domain of active research. So very recent papers are on that, so you can have a look. You just have to search just by typing that force free magnetic field regions in solar coronal plasma or in solar corona. Okay, now coming to another point. So this is the it's a very interesting phenomenon. It's called magnetoconvection. Okay, as we did for normal hydrodynamic fluid, Rayleigh-Bénard convection. So this is nothing but a generalization of Rayleigh-Bénard convection for magnetic fluid. More specifically for an MHD fluid. Okay, which is embedded in a background magnetic field B0 that was absent for a normal RBC. Rayleigh-Bénard convection. So in ordinary RBC, the convective instability is purely non-oscillatory in nature. If you remember the nature of the solutions, when the instability was setting in, then the system was totally non-oscillatory. But in MHD case, actually, if we are in such a situation that the magnetic diffusivity is less than the thermal diffusivity, okay, that means so if you remember, thermal diffusivity comes into play when we are talking about the the evolution equation of the temperature, right? So there will be an evolution equation of the temperature. This is equal to some kappa nabla square T, right? This type of thing. So if we have such type of equation and we have two diffusivities, one is magnetic diffusivity, another is thermal diffusivity. So if thermal diffusivity dominates over magnetic diffusivity, simply instability is possible to even start with the start in the form of growing oscillations. So that means that even at the very outset of the instability also we have oscillatory type of solution, but this oscillation actually grows in time, which leads to the instability. But if in the case where eta is greater than k, that means the magnetic diffusivity now overcomes the thermal diffusivity, then the convection can only start from non-oscillatory state, and that's exactly similar to the case of hydrodynamic Rayleigh-Bénard convection. Okay, and most of the terrestrial situation is exactly like that, because for most of the materials, okay, and most of the laboratory plasma, and also very often the space plasmas as well, the magnetic diffusivity is actually much more larger than the thermal diffusivity. Okay, now it is your task to find out some instances, or at least one instance, where eta is less than k. Okay, so I want you to do some research on it. So in such a situation, now in the Rayleigh-Bénard convection of an MHD fluid, which we call now magnetoconvection, we have two dimensionless numbers which are of prior importance. One is of course the Rayleigh number, okay, which mainly talks about the importance of the temperature gradient, and we also have another number which is the Chandrasekhar number. So this number represents the importance of the external background magnetic field. Okay, so you see that this Q, it's a very small and elegant home task to just verify that this is a dimensionless number. Okay, so if this Q is 0, then of course we have the normal RBC condition. But if it is non-zero, then for marginal stability, the marginal Rayleigh number is related to the dimensionless wave number. If you remember all these things, okay, are related by this equation, where R is equal to pi square plus k prime square by k prime square times pi square plus k prime square whole square plus pi square times q. Now if q is equal to 0, we simply have r is equal to pi square plus k prime square whole cube by k prime square. Now can you remember something? I hope you can. Okay. And then one can show experimentally, actually this was Nakagawa, who in 1955 actually experimentally found that for small Chandrasekhar number, what happens that the critical Rayleigh number for the magnetoconvection, critical Rayleigh number is the minimum value of the marginal Rayleigh numbers. Okay. Actually critical Rayleigh number tends towards the critical Rayleigh number for hydrodynamic case. But for large value of Chandrasekhar number, what happens that when the magnetic critical Rayleigh number increases, okay, so I mean when Chandrasekhar number increases, the magnetic critical number also increases in a monotonic way. What is the meaning of that? The meaning is simply that if your critical, if your Q increases, that increases your critical Rayleigh number, that simply says that for stronger magnetic field, you have to arrange for a greater temperature gradient, okay, to have a convective instability. That means starting convection is comparatively harder. Okay. Now, in fact, what happens? Why is this? Physically, it is because the convection tries to deform the magnetic lines of force and therefore the magnetic tubes of force, and therefore this is hindered by the magnetic tension, because magnetic tension does not entertain, to its best possible, does not entertain any type of sudden deformation of the magnetic lines of force or tubes of force. Okay. So of course now if your temperature gradient is so important that this magnetic tension effect is getting dominated, or how to say that, dominated, or overcome by the temperature gradient force. Okay, then simply you can have convection there. Now why this is important? Because we all know that sun contains dark spots on the surface and they are called sunspots. And one very popular question in space and astrophysics is why the sunspots are dark. Okay, so it is true that the sunspots are the place where you can see very strong magnetic field of the order of 3000 Gauss. Okay, so 1 Tesla is 10 to the 4 Gauss, so it simply says that it is nearly 0.3 Tesla. It's very strong. Okay, whereas in the solar wind the magnetic field is of the order of nano Tesla. Okay, so these due to this strong magnetic field, what happens? Okay, before that I have to mention one thing. This was for the first time found by Hell in the year 1908, and he found that from Zeeman splitting of the spectra of sunspots. And then he said that the inhibition of the thermal convection, okay, by magnetic stress within the sunspot makes this part colder. Okay, because the thermal convection is not efficient, so from the convection region to the surface the energy is not transported efficiently, and that gives this part a lower temperature, and that's why you see this part as dark. Okay, and that was proposed for the first time by Biermann in the year 1941. Now, just before going to another topic, let me just tell you that the dimension of the sunspot. So nothing maybe to do with that, but just for you to have an idea. So the sunspots are of course nearly 10,000 kilometers size, and actually you can see that there are sunspots in which the total Earth can actually go in. So Earth has a average diameter of 12,000 kilometer. Okay, so it can enter in. I mean, there are some sunspots. Now that was the reason for the darkness of the sunspot. There is another very interesting thing, that when people observed the sunspots, actually this person held, okay, he also observed it, and he actually found a very good explanation for that. He observed that most of the time, so not only him, but I mean, many astronomers actually observed that, but he was the first to understand this and to explain the reason. So they used to see that the sunspots are not situating in an isolated manner. So they are always, I mean, almost always, okay, very frequently they are found in couples. So, and there, these two couples, I mean, these two sunspots, they are simply located very near to each other, very close to each other. And then there you can see that there are, most of the cases you can see that the plasmas, I mean, a flow of plasma, I mean, of course, representing the lines of magnetic lines of force type of thing, is emanating from one of the sunspot and is just entering to the other sunspot. That means that these two sunspots are of different polarity. Okay. Now, these type of regions are known as bipolar magnetic regions, and they are very frequently seen. Okay. Now, bipolar magnetic regions, why are they formed, and why some plasma actually comes out from one side and to go to the other side? So, the reason is very simple, that in general what happens, that just above the surface you can see that you have some environment where the magnetic field is very weak. Now in this part the magnetic field is very strong. So in this part at the surface you should have a pressure balance. Okay, that's very common sense. And now if you see that here you have the pressure external is equal to pressure internal plus the magnetic pressure b square by 2 mu 0. So since b square by 2 mu 0 is very large inside, then Pe simply can be very greater than Pi. So the internal pressure is low, right? So you can easily see that I mean, the pressure E is greater than Pi, and if you simply just take for simplicity isothermal region or polytropic region, you can roughly say rho E of the plasma will be greater than rho I, right? So it simply said that you have a lighter mass of plasma which is inside, and a heavier mass of plasma which is upper in the, I mean, so which is under the mass of plasma which is of greater density. Then what will happen? That this plasma will try to get out due to buoyancy, and this is known as magnetic buoyancy. Okay, magnetic buoyancy. And then they just try to do like this, and when they just touch this surface, so then they simply gets out of a sunspot, and then of course in order to finish the, I mean, close the loop of the magnetic fields, then they enter through the other sunspot. Okay, now the exact, so that was only a very schematic definition of schematic explanation of what bipolar magnetic regions are and how are they forming. But it is true that the true story is much more complicated, and really it is still a matter of I mean, active or ongoing research, that what is the characteristic size of I mean, the relation between the characteristic size of a sunspot to the corresponding magnetic strength of that region, and why exactly the bipolar magnetic regions are formed in a much more details. So all these things are still ongoing, and there are subtle things as well. So if you are interested, I always will encourage you to go to any of the papers, recent papers on that. You have to just search. So mostly all these things are taking place in the solar surface. Okay, so you have to just search that magnetic buoyancy. I mean, like how to say that, the bipolar magnetic regions, this type of thing, and then or magnetic buoyancy in the sunspots, so bipolar sunspots, all these things. So just search with different type of keywords. This is a trial and error method, and you will come across a bunch of papers, and you can see how the people are trying to advance the understanding with time. Okay, so this is all about within the scope of this course. This is all about the brief discussion of the application or the importance of magnetic MHD equations. Of course, MHD equations are not that much used for galactic fluids or other accretion disks till now. Of course, there are works on the role of magnetoconvection for the effective transport in the accretion disk, but for the lack of time I am not going into that. There is this aspect. So the role of magnetic field in the efficient angular momentum transport in an accretion disk. And there is also another thing, is that if you remember that when we were talking about the model of the Parker's model of solar wind, we took simply a hydrodynamic model, and then you can simply modify that model just in injecting magnetic field, and you will see that there will be something very interesting called Parker's instability, and you will have the spiral type of structures which are forming. So all these things you can see in any standard book. So I am just telling you the names. So yeah, but within the scope of this course, I am just ending this discussion here, and from the next lecture onwards, I will try to introduce turbulence both in normal hydrodynamic fluids and plasmas. Okay, thank you very much.